we were discussing about linear models in the last class, and we saw overfitting as an important phenomenon, and also underfitting, where I hope in the exercise class today you had some good experience trying this out with a feature expansion. If you have like one feature, you can expand it into several more features, or already if you have several features, then of course you can expand many of those into even more features, and then do a linear model to classify or to do a regression. So that was one important part of the most important part of the exercise. And what we want to do today is to understand a bit more about what these models have to do with the data. And one very important concept here is the likelihood. So maybe several of you already know what a likelihood is, but today we want to study this concept to connect the data that we got with this model that we feed to the data, right? For now there's no connection here, so that's the goal for today. And then we will also discuss regularization and the rich regression. So before, what we did so far is kind of this classic machine learning approach that we don't care what the data truly is or where it comes from. I mean, okay, we should, but what we do in machine learning is that we often just take the data and just fit any model to it, and we don't do much thought of what is the probabilistic process of, or is there like a true model? Is this a good model for the data? What actually has generated the data? All these questions. This we have not thought about yet. So that's what we want to do today. We want to do this again for the example of linear models, and to ask for which kind of data are the linear models actually good models. And if you look at this data set, that's actually the data set I think that you also had in the lab for the width and height of people. There was this nice kind of correlation. That's one thing, though the red line looks like it fits well. So we will make precise what we mean by that today. And we are motivated by the following. So we are motivated by this plot here on the right, when we look at the errors. So this is how much is the true prediction, sorry, how much is just true value? That's the Y value. How far away is that from what the model predicts, right? So this difference here between the actual blue dot and the red prediction. So that's this difference, right? So here is my model, and then this one is the true yn, and the difference is what we call this en, of course, as always. So en is the difference, and now, so these are this en, and this is the histogram of all of them. So what the histogram is, right? It just means, yeah, for all my many samples, I compute the value en, and then I count how many do I have, right? So here is that. So here is a 0, and you see that most of these en values are around 0. So the most frequent error is small, and then you left and right you have bigger errors, and you can see that they become less frequent. So this histogram shows the frequency. So frequency to have the error 0 in the middle, or a +1 or -1, or any value you want to have. And what's interesting here is that this looks nice. First of all, it's centered around 0, and what's also very interesting is that it seems to decay very quickly, and it looks like a nice Gaussian distribution. So this should be a motivation to tell us, okay, maybe for this data set there's something particular happening. So maybe for this data set the linear model was a particularly good one. Or how could we explain otherwise that these errors, the en, I mean, remember, these are just the true values minus the model. How can we explain that they are so nice, that they look so naturally distributed like a Gaussian? So that's what we want to do today. And to understand, we just want to have two small building blocks. And so this is just a recap for probably most of you know this already, that if you it's just a definition of a Gaussian random variable in one dimension. So here we have a variable y, which is a real number. And we ask, what does it mean for such a random variable to be Gaussian distributed? And this, I think you have seen this. So here, sorry, this is the definition of the normal distribution. And he has two interesting parts which describe what a Gaussian is. One of them is the mean, and the other is the other is the variance. So mean and variance. So variance we call sigma, or sigma square if you want. And you can see that they also appear in the definition on the right. So this is the definition of a Gaussian distribution. And the point is that it depends on how far you are away from the mean. That's squared, so that describes what a Gaussian is. Sorry if that's boring. So you might have seen this already. I just want to do the recap actually for the more interesting case when we have a whole vector of random variables, and we say that whole vector is distributed from a Gaussian distribution in space. And now we have d variables. And so what does that mean? So maybe this one you haven't seen, or you might not recall in full detail. So I'm giving it here again. And again, we want to say that, so, I mean, either you could try to do this just independently. You could say every entry of my vector is distributed like this. This, of course, you can do. But then this only gives you a limited geometry, and you don't have the full freedom of how a Gaussian distribution could be located in space, right? In space, this Gaussian distribution looks a bit like a sphere or a squeezed ball or an ellipsoid or something. So that's what I briefly want to recap. But so to define it in full generality, you do this again very simply. So that the mean, I think, is pretty clear. So what does it mean to have a mean vector if you have some distribution in space? Of course, that's just a vector, right? It's just the average of all your samples. And so that's one important element to describe our distribution. And that's the first argument here. Then the second one here is now something a bit more funny, which is called the covariance matrix. So, and that's a bit strange. So I want to show this here. So here's the inverse, and then here it also depends. But this term here you don't need to think about much because it's just for normalization. So this one you can actually ignore. But what's happening here, this exponential, that describes how these points are distributed in space. So, and the intuition is very simple. So if maybe I have two directions in space, sorry, maybe I'm in two dimensions, then I have some kind of ellipsoid here, and this thing is centered at the vector mu. Sorry, mu. And then the shape of this thing, so it could be spherical or it could be a bit more squeezed. And that shape is described by the covariance matrix sigma. So the sigma actually describes this ellipsoid. So it turns out that the eigenvectors of sigma are describing which are the the main directions of this ellipsoid to describe where is your stuff distributed. Actually, if you are a bit confused by this, then you could just ignore the sigma for a second, and then what you have is actually then you just have here y minus mu. So then what you have in this exponential is just the difference of y minus mu, right? Squared, and that's it's just the distance from your mean, right? That determines your distribution. In that case is when you have a spherical Gaussian. So that's actually the same thing you get when the sigma matrix is identity matrix, which means everything is round and nice. And so the decay, how likely is your point happening is just how far is y away from the mean in the spherical distance. Now, if you add the sigmas, what those do is they just define a different distance, which is not spherical. So sigma has to be an invertible matrix, and those just define a distance in space. And that's also one different way to illustrate why this is an ellipsoid. So, but yeah, so don't worry too much. So we use the definition here. We don't require you to prove too much about the geometry of this ellipsoid, because for us the sigma is kind of given here. Also the mu is given, and then you have a Gaussian distribution, and y of course is the random variable. Does this make sense or a bit? Say again about mu. What the graph means. So what I mean by the round shape here would just be the frequency, right? So that the points which are closer here, they have a higher frequency under the distribution, and the ones further out have a lower frequency. So it will look like a hill where the highest frequency is in the middle. So that's what this graph means, and it's in the dimensions are y1, y2, right? So I have two dimensions, and I ask for each point here, I can ask how frequent is it under this distribution. This guy is most frequent, and then the further you go away from this ellipsoid, the less frequent you get, which is the same as here. Here is the center, the mu. If you go away, you have a lower frequency. So this then takes the role of the probability of this value, and the same. And for us, the probability here is I just draw this level set, so it's high in the middle and low as you go further out. So yes.
Why the y is potential of t, not potential of n? The y is just for each couple of x, then the y is just a number, one of the.
Yeah, that's a good point. So here I'm not talking about the machine learning problem yet. So here I just talk about the definition of a Gaussian, and you're right. So now on the next slide we will see how we apply it to get a data set, and then I think you're right. Then we will have n data points. Yeah, we will see, because the points live in d dimensions, and this Gaussian here lives in d dimensions. So I will get to this. Sorry. Here it's just a definition, yeah. So the Gaussians are defined in any dimension, and here we just call it d. So this is just two definitions: one Gaussian in one dimension, and two Gaussian in d dimensions or n dimensions. So but yeah, it's correct. So because this will be used for data points later on, and the data points live in d dimensions. So another question? Okay, so one small thing I also forgot to say: the definition of independence. Two random variables are independent if and only if. So this equality holds, like, yeah, the probability that they happen, so both of them happen at the same time, that's the same as the probability of one happening times probability of the other happening. So that's what it means for them to be independent. And this, of course, is a very important, the most important property that random variables can or cannot have. And that's also something we're gonna use. Okay. So let's see. So these are just some tools. Let's see what happens if we talk about data sets now. So what we now want to discuss is what does it actually mean for this data set to be corresponding to a good model, or what does this model even have to do with the data? And the one of the most natural ways to do is that, or what we have to do is we need to assume something about the data, right? Because if someone just gives you a crazy data set of some very special geometry, then it's very hard to say if probabilistically this is a good model or not. But if we have additional knowledge about where the data came from, then we will actually see that which model actually fits this data best, and which model explains this data, or here even which model could have generated this data. So is there some kind of true model which could have generated this data? And if so, our learning stuff, does it actually then find something which is close to this true model which has generated the data? So that's the viewpoint we have here. And so for now, it's just an assumption. So for now, we will just assume that what we have discussed on the first slide. So what if the true data came from a Gaussian distribution? So what could we say then? And that's written here. So we have this epsilon n. So right, what we say is that our y's are truly came to be by taking some unknown w and then multiply with the x's, and then adding some Gaussian noise. So assume the noise we added here is Gaussian. So is a Gaussian random variable. So this is just a number actually. Is Gaussian. So what then? The nice thing then is then we, if you assume this, then now we have a model which can generate us as much data as you want. So and what I mean by generate is just the x's have already been given, but now you have an explanation of how did the y's happen to be for any x, right? So that's the point, right? If you don't make any assumptions here, then the y's that your customer gave you, they might have had nothing to do with the x's, right? If you just look at the data set, you have no idea if there is a relationship between those y's and the x's, and both these you think are coming from a random process, but what is the connection? So that's what we here assume, that we assume nature is like this, that for every x we had, that the y came to be as this linear model plus Gaussian random noise. So and if I've now studied a few times, but we should actually formalize this a bit more precisely what I said. So what we mean by that is that we need to express this precisely in terms of probability, right? The y's are random. So, but in which sense? What's the connection? So what we said here is that the probability of y given x is, and yeah, you can also think it might depend on w as well. What we say here is that this is a Gaussian distribution. So this is a normal distribution. So that's what we assume. That and this, I mean, if you have this, then it's exactly the same. What this means here is that the mean of our Gaussian is this, and then the noise is sigma square. So a sigma square Gaussian noise. I mean, is there an equivalent way of saying this if you want to say something about the epsilon? So then could you say that the noise is from a specific distribution? It's the same as saying that this y's is from this distribution. If you know this, then what's the distribution of the epsilon? Can you tell me epsilon given the x and so I mean, the same thing would be to say that the probability of epsilon being whatever it is is also Gaussian, but has mean 0. So that's the same thing. So you can, maybe this is the main thing to assume, but equivalently you could also say this, that probability of epsilon is actually mean 0, variance sigma square. Okay, and why is this good? So for now we've done nothing. We have just assumed things, right? We don't know if it's a realistic assumption, but from our first motivation plot, it looked like for that data set, it looked like a reasonable assumption. But if we have this now, if we understand how the y's came to be probabilistically, then we can use that. And now we can talk about which model would have been the most likely one to generate this particular data set. Which model would have made sense for the data which the customer gave us. So the data we observed was this y given x, right? So I mean, we are interested in the y, the label. So how the y and x related, and this is actually called the likelihood of the y's given the input x and the model, right? So you can say if the model was w and the data was x, then what's the probability that we would have seen this particular y's? So that's what the likelihood means. So it's the likelihood of these labels y. And what is it? So y here is the entire data set, so all the labels of all the points, and x, of course, are all the points. And so now we have n data points, and each data point is in d dimensions. So what we assume here, of course, is that all these data points have come to be through the same process. So all of them have been generated using our model here, which we discussed. So this is what we call a generative model as well. So I'm saying the probability that we see all these y's together with all these x's that's here is the product of the probability of each of these data points. So that's what's happening here, and that's why this is inequality, is just because independence. So I just mean that every point has been generated independently from all the others. So that's why we just need to understand how to generate one point that's here. If we understand this, then we understand also the whole data set. If somebody gives you the entire data set, how likely is that data set if this were our true model W? So Okay, so this is the probability of one data point. And this we know what it is. That's just what we wrote here, right? So we know how these get generated as a random process. They are normal distributed. So that's what it's exactly what I just plugged in here. So and yeah, so this is the assumption. On the noise, or you can also call it the assumption on which we made here on our wise. It's the same thing. So okay. So what we have now is that for any model W, so we can now ask if W were the true thing that has generated this, then what would have been the probability of getting this wise? So that's what the likelihood tells you. So we don't know what W is, right? That's a bit the point here. We see the X, we see the Y. We don't know what W is, but we know that there is a W and such that the real data has come from this random process. And now we can ask, yeah, which W would actually have made this particular XY most likely? So and that's what it means to find a model which maximizes the likelihood. So ask which W would have been the most likely one to generate this particular XY combination. And yeah, don't worry. So it will become more clear on the next slide. So when we then later on, we will see that this motivation will lead to the exactly same thing of what we did before when we minimize a loss, right? So here we do a different thing. So here we say, oh, maybe it's a good idea to talk about that W, which maximizes the likelihood of our data. And we will see later that these things are the same things, if you have this assumption on the data that it comes from a linear process. So that's the goal of the next slide, that we want to see if there's a connection between cost and between this likelihood we have talked about. Don't worry about the log for now. So we will do this step by step. So it's very simple. We will compute what this probability actually is now. So here we just saw that, yeah, it's normal, right? But now we will plug in the definition of the normal distribution. We will see what this probability actually is, and then we will see that maximizing this thing, which is called the likelihood, will be the same thing as minimizing the cost. So that's the plan on this slide here. So I will just basically restart from the previous slide where we had the probability of the entire data set. So I mean the Y is given if you have X's and the unknown W. So what we said on the previous slide was that this is the product over each point happening separately. So each small n and small xn together with the Y. And the product is from n1 to capital N, of course. So this is the same thing. We did that before. And so what this actually is we said this is normal distribution. So the Y's are normal distributed along some mean. The mean is X times W. And there is a variance. So that's what we assumed on the previous slide, right? So all the same thing. And again, the product over N. Okay, so now I need to plug in what does it mean? What is actually the definition of this normal distribution? Let's see again. So it was some crazy constant times the exponential if this were just a number. and that's what we need here, because our yn is a number, so we don't need this complicated shape for now. We only need the number. That's good. That makes life easier. And for this here, I will just write a constant, right? So it doesn't matter so much what this scaling is. But what we need to remember is the exponential of the distance of y and mu. So minus the square distance of y and mu. So that's what we're going to plug in now. So some constant, I call it c tilde, times the exponential of minus x times w, that's the mean. Okay, sorry, I want y minus the mean squared, just for notation. It's getting a bit cramped here. I'll start again. It was the exponential of minus y minus the mean. The mean is x times w. And then this was squared. And then it was divided by sigma squared. It's not so important, but that's the scaling which we had in the definition of the normal distribution. And there is a 2, maybe I forgot. So, and yeah, remember there's a minus here. Okay, is that correct? I hope. So, yes, that's good. And what's still here is this product. And that is very annoying. So it's kind of annoying to deal with this big product of the n data points. So we want to do something to get rid of this. And what you can do is, instead of talking about this quantity, you can just talk about the logarithm of this quantity. So, and that is what's called the log likelihood. So I just put a log in front of it. So this thing we already know, right? But talking about this, I can also talk about the log of the same quantity. I'll put logs everywhere. And also here. And now something nice happens. So that this product gets more manageable. And if I write this down, actually, so the log of the product is the sum of the logs. So sum log of still this thing here squared. And yeah, that's what it is. And the sum goes from n small one, small n goes from 1 to n. And also what happened to the C stuff. So that's, I ignore this because that's just going to be a constant. Well, because that C again here is a product of, so sum and log of products are sum of logs. So here's a sum of a log of a constant, whatever, and here's a sum of the other logs. So this looks correct to me. And of course, the only thing that we really care about is that the log and the exponential have disappeared. And now what really remains is only the nice part, and that's the part here, right? The distance of y minus the mean squared, so y minus the model squared, that's of course the crucial term. And to be honest, I also forgot the minus here, right? You can keep the minus here, but nicely, because log and x they kill each other, this all disappears, and I can take the minus in front here. So that's why in the final thing there's a minus here, and we are done with this. small computation. So what is the takeaway? So the takeaway is that the log likelihood, which is the whole thing, is something that we're already familiar with. So, and this is the yellow thing. This is actually something that we all know, right? The yellow quantity of each data point is the cost function we all know, right? If you put mean square cost onto a linear model, then that's what the yellow quantity is, right? Including the summing of all data points and so on. So this looks really much like mean squared cost, but here, I mean, what it is, it's the log likelihood, right? So that's why we have found a very different interpretation of how these two very different concepts are related, right? The log likelihood. So how likely is this data if this is my W? If I want to talk about that, the resulting quantity is the same as if I talk about a W and ask what is its loss or its cost function. So in this special case of linear models with least squares. So yeah, is the computation kind of clear or too slow, too fast? Any question? Okay, to summarize, we will compare the two quantities. So that's here, the log likelihood. Log likelihood of this model is this, what we just computed. And then what we're already very familiar with is the cost of, I mean, MSE, right? Mean squared error. And they are basically the same thing. So that's what we want to say here. And except that this one has a minus in front of it. And then this is also a problem here. So what about this? What do you think about the constant if we say maximizing the likelihood or minimizing the cost? But then here we have this difference. Is that a problem or not? What do you think? Exactly. So I hear it's not a problem. You saying this constant is independent of W, and that's exactly true. So what this does is it doesn't matter, right? Because I mean, what we will do is we want to maximize this log likelihood. So maximize it. And in all the story last week, we want to minimize the cost. So. And all this is, of course, over W. You ask which W minimize the cost, which W maximize the likelihood. And so this is caring about the argmin or the argmax, right? Which W. And you can see that must be exactly the same one. Because, of course, it doesn't matter if you minimize, maximize something or that same thing with a added constant to it. Okay, so we see that these two things have the same solution, W. Of course, you might have several solutions, but yeah, they're really the same optimization problem. Maximizing the log likelihood or minimizing the cost function. Any question on this?
So how do we know the variance of the data, or we just neglect it?
That's a very good question. How do we know the variance of the data? So this sigma square. So yeah, this is, I mean, that's a good point, and I could not give you a easy recipe to know the variance in the data. I mean, you could empirically estimate it from if you look at your data set, you have an empirical mean, and so that's if you just average all the y's you have, and then from that you could also look at an empirical thing of sigma, but it's just an approximation, right? Because here we pretend that this is the true sigma, which has generated as much data as you want, right? So this sigma is for the true random process, which has generated your data set, and yes, we don't know it. So here we just assume there is one. And yeah, so this is a scaling of our objective function, and yeah, we should maybe not forget it. That's true. But also the scaling, it will not affect what the minimizer is, right? If you minimize a function, or if you minimize 10 times the function, it's the same thing. So both the constant and the scaling, they have no effect on what the best W is. But thanks, yeah, I forgot to discuss that. There are two differences. This is different, and this here is also different. So thanks a lot. Yeah.
Is there a reason that not likelihood at the end we compare it to MSC, not MAE, for example? Why did we compare it?
Yeah, that's also a very good point. So you're saying why MSC, right? So why? I mean, because when we did this story today, we had nothing about loss functions, right? We just said, okay, the true data has been generated through a random process, which happened to be Gaussian. So why MSC? Well, it just happens to be only for MSC you could claim that this is the same. So now the question is like, what if we have another cost function? Could there be another random assumption you could make on your data such that those then correspond? And yes, for some other cost functions, there is sometimes there is a similar assumption you could make how your data is generated. And one interesting one is not this one. So this one. So what if my data comes from a different distribution? For example, the so-called Laplace distribution. That's also something you can assume. So what we have here is that we pretend that the y's that we observed, they came from a Laplace distribution around the same mean, so linear model. But now again, the distribution is a bit different now. So now you could do the same argument as we did. Now you ask, okay, what's the likelihood under this model? How do I maximize it? And what you will then get is actually then you will see that this will be cost function of actually the mean absolute error. So right, which it looks a bit like that, right? Because the thing in the red part is actually the mean absolute error. So, but we're not gonna do this one in full detail. It's a bit of a computation, but this is the absolute error you are familiar with. And if you do the computation, you can see that likelihood. So the likelihood of a model under this distribution for this linear model, maximizing that is the same as minimizing the MAE. So but then if you have any cost function in general, then I cannot tell you what distribution would have generated it. So this I don't know. So yeah, this is quite specific. It's very specific for linear models. It's very specific to what you assume on this noise, right? Where it's a strong assumption. It's not clear that you can make this assumption that nature has generated all these errors in a Gaussian way or in a Laplace way, right? This is a strong assumption. But that's assuming that your data fits a linear model is also a strong assumption. And here you see, it's actually kind of the same assumption, because maximizing this likelihood here is the same thing as minimizing the cost. And that again is the final summary of this part. So yeah, just for some specific data set assumptions and some specific cost functions, you can get this connection. Okay, so now we have two understandings of linear regression, which is nice, at least for the Gaussian case. But of course, there is more interesting models we can discuss. And after the break, I will very briefly tell you one more generalization that people can use if related to your question. It's interesting if there's other distributions and so on. And then in the last part, we will go to talk about ridge regression and regularization, which is also a very important concept and which you can also play with in this lab. So see you after the break. Okay, we finished this discussion about the connection of the likelihood and then the loss function on the other hand, right? So for some specific models, these are the same things, right? That if you ask which model has the smallest cost, the same thing as asking which model gives me the maximum likelihood. Likelihood being that observing this data y, what's the probability of that, right? Observing this data y, if that's my x in the model, that's what the likelihood is. So, and yeah, so there's kind of, why is this useful? In practice, not so much, but it gives us a way to interpret why are we doing this, right? It tells us that yeah, this makes sense, right? Because if I do this, then I get the true model. Here I get the W, which is the one which truly explains the data, right? In the sense that that data is most likely if I have this probabilistic model of my data, right? And then if you do this more generally, right, of course, it's not true for any specific cost function, but it gives us a different way to think about cost functions, because some people don't just define them by hand, but they define the cost function motivated by the likelihood. So, and then you still have to make strong assumption, right? Instead of just handcrafting a cost function, you would say, okay, I will just assume that my data comes from this kind of random process, from this kind of distribution. If I make an assumption on that, then I can get a likelihood. And then I can say, okay, now I want to maximize this likelihood. So, and one reason why this can be a nice thing is this connection that is their connection to the true model, right? We only see a small sample of our data set, only n points. But here we're talking about a random process which can generate infinite data. So what's the connection there? And that's something I will just tell you very briefly here, that there's different things, right? So the likelihood we had before was just the sum of these so the average of these points y given x in the model. So and here we just go small n from 1 to capital N. So this is the maximum likelihood if you just have n data points, and here is where you make your assumptions, right? So here you assume that you know how your data has been generated. So we just did one example of that. Of course, you can make all the probabilistic assumptions how each data point yn has been generated. Now, but what we want to do here is we want to compare this to this other object, which is this one, which is the true likelihood or the expected likelihood, and that's the one which you would have if you would get an infinite data set, as much data as you want. So the question is, if you just have n data points, or if I have this kind of true data set when I get as much data forever and ever, then I have an expectation here, and that's called this expected likelihood. Now, what do they have to do with each other? So this is kind of the first one. I will call it the maximum likelihood. Just the finite likelihood, and the other one is the expected one. And what I'm saying here is that when you get more and more data, then they do the same thing. I mean, of course, the quantity becomes similar. But what we're really interested in is not this quantity. What we are interested in is the model. So So, and what we can ask here is, and that's what statisticians ask, is this W we get when we maximize this for finite data, does it have anything to do with the W that truly generated the infinite data set? And the answer is yes, they do have something to do. They actually converge to each other, right? So from this infinite likelihood, you get the maximizer of it will be something that we call W true. And then if you just do it on finite points, then you get something. If you maximize that, then you get what we did, right? Then we just got the W, which is called MLE. And the point of this slide here is to say that when you get more and more data, then those they converge to each other. And so that's what's written here. They converge to the same vector. Have to be a bit careful what convergence means, because this is a random object. But the fact that they converge to each other, that fact means that this estimator here to find the W, that is a consistent estimator because it goes to the true one. So that's what consistency means for those of you who are interested in statistics. So just to motivate this even a bit more. And then there's some more literature if you're interested to how you can prove this. When does this happen? For which kind of probabilistic models does this happen? So, okay, so here we just state this as a fact that they converge, and by convergence I mean in probability. So with high probability that they become similar, and yes, that's actually what I wanted to say here. And then, yeah, if you want to be more precise, then people also asking in which metric are they converging. So that's also something that you could look at. Okay, any question on this? So that would finish our exploration into statistics, right? This is really a bit of statistics view, what is the likelihood and so on. So now we kind of switch back to machine learning and ask more again. We don't make any assumptions on data, so we just are more empirical, more engineering approach that we just say, I will just engineer my cost function, and if it does well in terms of test error, I'm happy. So that's more the machine learning approach. And this approach here is more mathematically rigorous, but more complicated, that we need to make strong assumptions on the data. Yeah, that's what you wanted to say on likelihoods. So any question on the chat? No. Good, then we can switch to this small chapter here. And I think that's a very important one, which is about regularization. And I mean, on one hand, it's on two kind of variants of linear regression, but then much more fundamentally, regularization is something that's very important, and it helps us to go to good models which do not overfit. And this will also come again then next week when Nicolas Flammarion will talk about model selection, right? Which model is the best? And that's something that you can also play in the lab actually this week to see what's the effect of trying to go to simpler models and not too complicated models. So the motivation here is that if we just minimize the cost function, so that's like the fit of our model. So L here is any cost function you like, right? So this is just very general here. And what we saw is that there is often a problem, right? Often our models are kind of too powerful in the sense that they can fit any data perfectly. They can fit the data with loss function 0, or depend how you define your loss function. They can fit the data super well. And talking about the training data, right? But that doesn't mean that on a test data they might do a good job, right? So they might do too much fitting and then actually lose track of the underlying pattern, which is the true pattern, and not just the small noise that's also present. So that's what we had on Tuesday when we talked about overfitting, right? So what we do here is we try to counteract this overfitting. So this can be a bit too much if we focus too much on this. And the way we do this is that we also add a second term here, which actually punishes you if you choose a very complicated model. So it punishes for the complexity of the model. And we have to see what that means. So how to measure if a model is complex or not. But if we have such a measure, then we can say let's add this additional term. So I mean, you're very familiar with the cost functions already. That's the yellow part. But now we say we want an additional measure which tells you, okay, this is a nice easy model and has a small number, small omega. And if you have a very complicated model like the one we had when we were overfitting, hopefully the green term can be a large number so that you are discouraged from choosing it when you minimize them together, right? So you change your training now. It's not just L, but your training now is two objectives which are added. Of course, we have to discuss the strength of these two. But then you say we solve this. It's a bit like a multi-objective thing, but the two objectives are just added. So that's what you want to do, and this is called regularization. So that's what you want to do, and of course that doesn't say much right now. We really need to say a bit more specifically what could be such functions, and you could already guess maybe what be some easy ways to say if a W is giving a complex model or an easy model. Of course, it depends on your model architecture as well. So. Okay, but of course, the simplest case to do this is always to, for example, start with a square norm, and that's what we're going to do here. Here's my regularizer. I just set it to be the square norm of my model. It intuitively kind of makes sense, right? If the model has extremely large weights, then you would say it's kind of strange or complicated. If the model W is very small or short, then you would say, okay, it's an easy model. So it's just one way to measure model complexity. And this one we will discuss for linear models now. But you can use this for any model. You can also, this is actually also used in neural networks, where W are the weights of your neural network. Even there, you could say, okay, I want my weights not to be too large, so I will use this norm, Euclidean norm, as a regularizer. It's actually still used in most state-of-the-art convolutional nets for image classification. They also use this. So, okay, and what's the intuition of this? Not so much, just that the large weights will be penalized. So of course, if one of the weights or some of them are very large, then this becomes large. So really, this is just the sum of the squared entries, right? So that's the definition. Forget about the 2 here. That just means we call it 2 norm, but it's just a Euclidean norm. Okay, so let's see an example. Let's do this. Let's do this for one of the models we know well. And there's a question. Yeah, why do we consider a model is too complex when the weights are large? It's a tricky question. I don't have a perfect answer. It's just one way to measure it, right? It depends what model architecture we have, and then, I mean, you're right. It's a very hard task to, if you see all the models that people have, right? I wouldn't be able to sort them for you by complexity. It's really hard to express how complicated is a model into a number. So yeah, I mean, this is just the most naive way, right? I'm not saying this is the best way. It's just a very naive way to say, and we will see when we do it. We will see that there's actually an interesting effect, and it makes some things a bit nicer. It makes it actually easier to find this model, and yeah. And you can, if you try it in practice, you will actually also see that it works pretty well. Again, this is a bit the machine learning approach. You just try everything and see what works well. That's why this is used in deep learning. But for this particular one, there is also a very rigorous probabilistic interpretation, like we just did before. There is also an assumption that if my data is from a true model like this, blah, 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 then this will actually be the best thing to do. But this we actually don't have time to go in detail, but there is a justification for it in some special cases. So, but for now, let's just try it. But we still try it on paper. So, and if you do this, then the name of this thing is rich regression. So, so the whole thing together here is called rich regression. So here's the rich regression problem. So this is again, this is for linear models. It's for linear regression only. I mean, of course, this regularizer you can use for any model you want, but let's look at what if we use it for linear regression. And this is the problem. And yeah, this, of course, we are familiar with already. So, and you can already see that it's maybe there's something going to be convenient here because the squares on both sides. So we see this is going to maybe help us to discuss what's the solution of this thing. And of course, this part here is the loss of W. And then this part here is the regularizer. So which we say this is the most naive way to capture how complex is my W. And then the lambda here, we didn't discuss much. That's something we also have to consider. So how strongly do you want to balance these two objectives against each other? Do you want to have very small W's, then you pick a large lambda? Or do you want to have a very good cost? You don't want to be influenced too much here, then you pick a small lambda. Okay. By the way, there's one more special case. If you pick lambda 0, of course you can do that. Then you're back to least squares, so which we discussed already. So linear regression with square loss. We know how to solve least squares. We had 3 algorithms, right? We can do grid search, we can do gradient descent, and the third one we had a closed form solution for least squares. So this brings us to the next part. We could now ask, is there also a closed form solution for this one with the 2 of them combined? That's what we want to check now. But don't worry. I mean, you can always run gradient descent on this if you're not sure there's a closed solution. That's also very much the machine learning approach. We will always just use full creativity in what model we use, what cost function we use. But then we have this rather naive algorithm which we apply for everything, which is gradient descent. But here we are a bit more smart. So here we will look a bit more closely at the model and we will see, okay, for this one, you actually also can find a closed form solution again, which would be convenient. So which means also this one you can solve on very large problems very efficiently. And we're going to see how. Yes, before I want to say that, okay, with the lambda, right? So maybe I should write this not to forget. So it's very important if the lambda is very small, then this has no effect. So I want to say that if you have this, then you are in the regime where you're potentially overfitting, right? So. And why is that? Because you put everything you care about is the cost, and we have just discussed this already, that overfitting can happen if you only have the cost. And then the other one, if the lambda becomes extremely large, then we care only about this model being very small. what then will happen is actually underfitting. Because the model will actually go to 0, which is probably not the smartest model. So this is going to happen for sure if you pick an extremely large lambda. So, and yeah, this case here is when you have no regularization. So the regularization disappears. Okay, this is important that you understand the lambda, right? If it's very small and very large, and this is also something you should do in practice. You should play with this lambda, see that you can get the two things. If you see both phenomena, then you know that the best thing must be in the middle of the two, right? So then you know that you can find the right regime, and that's how you're gonna find the best lambda. And that we will discuss next week, right? What do you mean by best? This is gonna be the test error. Usually, which is going to tell us which one solves our problem, and also what we mean by overfitting, right? We never formally defined it, but what we mean by overfitting is exactly this: that good training error, but bad test error. That's what we mean by overfitting here. So, okay, so now how do we solve this for rich regression? And this is quite simple. Maybe, yeah, I can ask you. So actually, it's cheating a bit. The true solution is here. So there's some inverse happening and so on. So how do you think that this result came into place? So how do you think, or what would you do? What would you do if I ask you what's the W star, the best W for this problem? How would you find it if you had to find a closed form solution? So, yes, setting the derivative to 0, right? And yes, exactly. So how we got this one? So and it really encourage you to do it is by the first order optimality condition, which is exactly what you said, right? So optimality condition, which is just setting the gradient to 0 and checking that the function is actually convex. So we ask, is P convex? And then we ask, please give me a point W where the gradient of the function is 0. And then if we have this, then W is optimal. Well, then we call it W star. So okay. So this we said already, and now, oh yeah, what's P, by the way? P, of course, is the sum of L and the regularizer. Yeah, P is L plus omega. The cost plus the regularizer. Okay, so what we need to do is we need to take the derivative of this. So we already know what the derivative is of the least squares cost. We also know the derivative of this. So the derivative of this is 2 times W. And of course, I just need to sum them up. And then I set the derivative to 0. And what you then get is this solution. I hope you believe me, because I haven't done the whole computation. So there is an inverse here. Yeah, let's actually do the computation. It's very important that you have the right intuition to do some small computations like this and understand how to take gradients of these vector valued functions. And this one is easy for us because we already have the building blocks, right? So what's the gradient of L? We remember this. It's minus 1 over n times the data matrix transposed times the error vector y minus xw. So this is the gradient of the cost function, which you, and yeah, it's really good for you to recap what happens with these matrices and vectors, right? So this is a sum over these x vectors, and then you write it in matrix form, you get this nice expression. And yeah, the derivative of the regularizer is much easier, so that's trivial. That's just lambda times w, maybe a 2 lambda times w, if you agree with me. Then, and then we just need to sum up the two. And we want to solve for w. So if I sum up these things, so then I get gradient of p, and I want this to be 0, of course, and gradient of p of w. And what it is yeah. So you add them up, you get gradient of p, and you want this to be 0. And this is equivalent to saying that, yeah, just the sum of this and this is 0. So that's what I'm going to do now. And you can check that this is. So here I'm taking the w terms on one side. So this is x times this. This is one term, and then there's another w from here. So let's take together what's everything which depends on w. So here's the identity matrix times w, and then what's the stuff which does not depend on w? That's only this part here. Which is x transpose y. And there is some bug here. It's not the same lambda here. So I was cheating a bit because this is a 1 over n, right? So here's 1 over n, and then the other thing depends on lambda. So you can just define a new lambda, which is whatever the old lambda times n or divided by n. It's some number, and that scaling will be the scaling you have for w, right? So the same thing is I could just multiply all my sides by n, and then I get this expression here. And when you solve this for w, then you get our solution, and that's why we had this crazy expression here. The optimal ridge regression solution is this. And why is it that? Because the computation which you just did, and then you solve the linear system, and you arrive at this solution here. Does this make sense? Yeah. Say again? Where did the 1 over n go? Yes, sorry, it went into here. So I defined the new lambda prime I defined to be lambda times n. So I just renamed the lambda. So the n went into the lambda prime. So you had a question?
The axis and the y's and the variance of the axis. The regularization we add that line. Do we lose completely the interpretation of correlation?
Yeah, you asking when you did not have the regularizer, then there was the expression was easier, right? We had this nice correspondence between the covariance matrix of x to explain the labels. So now we have this strange lambda identity here. So what does that do? And this we'll actually discuss now on the next slide. So I will, it's for the interpretation of the W, it's not so clear what the effect is, but I will tell you that it makes it much more convenient to solve this. This is actually an easier problem to solve than if you don't have the lambda. So it's a more numerically stable thing. So it's much easier to solve this linear system than the one we had without the lambda. So. And this is what we have here. So, and this is very simple, right? Because remember, least squares we already discussed, right? In the least squares case, we just solved the linear system with the XX transpose, and we're done. And now we kind of have a modified matrix now. Now we're talking about this matrix, and we solve a linear system with this matrix. So the difference between the old matrix here and the new one is only that this lambda has been added, or lambda prime. So, and in which sense this is good? So what this says is that the new matrix from here has actually better eigenvalues, which means higher eigenvalues. So the condition number of this matrix is better. So it's going to be much more easy to find a solution because it's going to be more stable. There will not be a zero eigenvalue of this new matrix. Whereas the old one, of course, can have zero eigenvalues. It's very realistic and often the case. We discussed this, right? In both regimes, no matter if more data or more features, either way, you can have zero eigenvalues. It's very possible. Here you cannot, because even those which were zero, they get now shifted. So because you add this lambda, every eigenvalue also gets shifted to become larger by exactly this amount. So this is called lifting the eigenvalues. That means that in the new matrix, you do not have any zero eigenvalue, which is good, because then we can for sure invert it nicely. And yeah, to see that this is, I mean, you can prove this, that the eigenvalues of the new matrix are the same as the one of the old matrix, but everything is plus lambda prime. So, and that's what we have here in the proof. The proof is very easy. You look at the singular value decomposition, and sorry, eigenvalue decomposition, because this is a symmetric matrix. So, and I'm talking about the eigenvalue decomposition of this X covariance, and the eigenvectors are called U. So if you write this here, then this is your X transpose. Sorry, X transpose X. And then identity. You can also write this because these are orthogonal. The eigenvectors are orthogonal. So what you have here is that now you have obtained something which has the same eigenvectors because now we have a diagonal matrix here. So you have found the eigenvector decomposition of the new matrix, and you have seen that it has the same eigenvalues S, but they're all shifted by lambda, so they are higher. And if you want, there's even a second proof if you're not convinced yet here. So here S is the matrix which collects these diagonal entries, D or whatever the dimension is of this thing. So it's actually N, I think. So okay. So we have what I want to tell you here is that this matrix is easier to invert. So that's all. Than if you don't regularize. So if you have a strong regularizer, then the lambda prime is big, and then it's even easier to invert it. And that also means the solution is very well behaved. The solution will always be roughly in the same place, even if you change the X a little bit. That's what it means to be well conditioned. And if it's ill conditioned, then it's almost not invertible, and that means that small change in the data could make your solution W jump around by a lot, but this cannot happen here. Here it's very stable because the linear system here is better conditioned by how much better? Exactly by lambda, because the smallest eigenvalue is a bit bigger. It's lambda prime bigger. Okay, any question on this? Okay, I think, so now we have a very good understanding of L2. So L2 as a regularizer. What if I use L1? That's the next thing we want to discuss. And that's, of course, the next kind of measure you could assume on how to say if model is complex or not. You can, of course, use any norm as a potential regularizer. You can use other things. It doesn't have to be norms, but norms are just, again, the maybe most straightforward thing to use here. And so I want to mention the L1 norm because it's a very important. It's maybe the most widely used regularizer. It's used even a bit more than the 2 norm, I would say. And this is for a reason. It's a very specific reason that actually, if you do this with any model, then you get sparse solutions. You get a W vector which is sparse, which means has very few non-zeros. So that's what we want to discuss here a bit. Yeah, by the way, the L1 norm is defined. Yeah, it's also on the bottom of the slide. So it's just the sum of the absolute values. Okay. So this encourages sparse solutions, and this statement is true for any models, not only for linear models. So this is used much more for any kind of models. You can add such a regularizer. It's just that only for the squared cost. Only here we have a very clear understanding of what it does. So and so yeah, what I think you might have seen the L1 norm already, but here it's a bit special that we combine the L1 norm with these two with the squared loss, right? So this 1 and 2 are kind of combined. So that's going to be interesting here. You have a question? Yeah, that's right. So you're saying that the W weights which I get from this, they will be sparse. That's right. And what that means is what you say. You said that then only very few W's will be active, right? So only a few features will even be considered, right? And that's actually why this is interesting. It sounds quite drastic, right? It means that you're right, right? Why are you concerned, right? You're concerned because if this is sparse, then it will ignore most features, right? It's true, but that can actually be a good thing. So because in many applications we have a huge number of features, and then I think we were also saying, yeah, why is large weight a good measure of what's a complex model or not? So maybe you would agree with me that a sparse model would be maybe something quite nicer, right? So having only few weights, that's a better measure of simplicity, right? If I only have like 3 active weights, then maybe most of you would agree that this is a simpler model because it uses only 3 features. It has only 3 non-zero weights. Using only 3 features is a simpler model than a model which uses 1,000,000 features. So that's why sparsity of a model is a really nice measure of complexity. It makes a lot of sense. It also gives perfect interpretability, right? Because then you can say, okay, I was able to explain my data with only 3 features, so 3 non-zero entries in W. So that's nice. In many cases, will not be possible, but if you find such a model which is sparse, then obviously this will be a much more interpretable model than the one we did with L2, where here everything was dense. So sparse models are nice, but of course it makes it a bit harder to fit. I'm not saying that every problem can be solved by fitting only to 3 features. But for example, in genetics data, this is extremely often used because so if X is the gene expression of a person, for example, then it has like a few million entries in one of the X vectors. And you don't have so many patients, right? There's like, maybe there's hundreds of people in this medical study, and each of them has 1 million features. So you're trying to find this W with 1 million entries. You only have 100 data points. And then what people do is exactly this. So because they say the problem is completely underspecified, so at least then if you give me such a crazy model, please at least give me a sparse one that uses very few features. And then there is also theory that's saying if there's actually a true sparse model which has generated this data, then under some circumstances this problem here will find you the true model. That is also, so that's in the genetics thing. This is called the genome association studies or so, which kind of use this to find, and this also for interpretability reason, right? And W will find those non-zeros which explain most of your phenomenon. So you do regression for interpretability, which if you remember, this was our starting point of regression. This is one reason why you might do regression. And then this problem is also the problem which is the compressed sensing. For those who know, if in signal processing, this is also extremely widely used, because if the true signal is sparse and then some noise got added, then with this problem you are able to sometimes recover the true signal. So, but we're not going into this. So for us, the takeaway is just that this is sparse, so it's encouraging sparse solution. So I'm not going to prove that this is the fact. So I'm just, it encourages sparse W. I'll give you a little intuition, but not a proof. And the intuition is this one. So this is the L1 ball, which consists of, well, all the points which have small L1 norm. So this is how it looks in 3 dimensions, for example. It looks similar in 17 dimensions. I don't know, maybe. So these are all the points which have small L1 norm. You put some value, right? So points of small L1 norm. So that's the green part of your objective. And then now what you also have is the loss function. So maybe our cost function is somewhere here. Here's the point which has smallest cost. If you go further away from this point, it gets a larger cost. So what do we do to satisfy these both objectives? So how can we make small cost? So this is the L, right? So L of W. Make this small while keeping this small as well. That's what we're doing here. So here are these level sets of the L. So here L is 3. Here L is 2. Here L is 1. So it gets better the more close you are to here, and it gets worse the further away you get. So you want to be as close as you can to the center, but you also want to be in the blue ball. So what do? To satisfy the first time when you kind of satisfy both constraints, that the cost is still okay, and you satisfy the L1 constraint, so you're in this norm ball. That's, for example, here. And this, I'm just saying that this is not a coincidence. So here is your W star, which has kind of small L1 norm. Yeah. And it has reasonable cost. And this is kind of what's going to happen. What's happening here is that this is kind of like an ellipsoid which grows and grows. And then this the L1 norm has these spikes, right? It has a lot of corners and edges. So what's happening here is that when this ellipsoid first touches this constraint set, that is very likely to be at the corner, and that's why we get sparsity, because the corners are sparse. So every corner here has only one non-zero entry. I mean, maybe it also will touch here at the edge. Then there's two non-zero entries, it's still sparse. But it's very unlikely that this ellipsoid will touch the blue constraint set in the middle of the. So this will be a point which is dense, right? Everything is non-zero. This is a point which has two non-zeros, it's kind of sparse. And this is one which is very sparse. So this is why the L1 norm encourages sparsity. And yeah, this is just intuition. And if you want to read a little bit more, there is a small explanation in the slides as well. And that's all for today. And next week we have Nicolas Flammarion, which talks about model selection. Thank you.